As we continue talking about geometric transformations, we're going to discuss reflections. And what we want to be able to do is develop the definition of a reflection using construction, describe the properties of and write rules for reflections, and determine the image or pre-image of a figure after a given reflection. And remember, our pre-image is where we would start, our image is where we end up. We will be talking about a line of reflection, and as you can see here, what I've got this preliminary drawing, and this blue line is going to reflect my line of reflection, and we'll call that line L. And first thing we're going to do is we're going to, reflect this poorly drawn trapezoid over the line of reflection, and then we'll talk about perpendicular bisectors, how they work into it. So as we continue here, my perpendicular bisector is going to be a line array right here which intersects a segment and is perpendicular to the segment at its midpoint. That's important because our reflection is going to be equal on both sides of our reflecting line. And again, that line of reflection is going to be a perpendicular bisector of the segment joining each part of the pre-image to the corresponding point on the image. And we'll show that mapping here momentarily. So we want to remember that when we have a rigid transformation, the image and the pre-image are going to be congruent. They're going to be the same. So what I can do is start to identify some of my congruency markings to help tie those things together. And what I'm doing here is I am creating markings to where we can see that this is going to be a trapezoid. Hopefully, of course, I'm not drawn to scale, and that's why we use these congruency markings, because we're not perfect drawers. But hopefully you can see that this is a trapezoid if I were to draw the image over here, and that I have these two sides are going to be equal, these two sides are going to be equal, this angle and this angle are going to be congruent, and these two angles are going to be congruent. And there's some other definitions in there, but in the end this is going to be a trapezoid. I'm dealing with some definitions that we haven't quite covered in class yet. But what I want to see is I want to see that these are going to be a rigid transformation. So our image is going to be corresponding here, that this is going to reflect to, this is my, if I have, I have my new image forming here as I show the reflection. So what we have forming here is that C maps to C prime, not C comma, bear with me on that one. And then B maps to B prime, A maps to A prime, and D maps to D prime, and that is being reflected over this L axis. But to show proper reflection, what we're going to do is we're going to look at this next drawing, and it's going to see that it's going to be a little bit more specific. Here, this is intended to be a reflection, and we can see here that B maps to B, B maps to B prime, C maps to C prime, A maps to A prime. And what they've added here, of course, my image and pre-image, this is, and of course, stolen off of math bits, this distance and this distance from B to the line of reflection and B prime to the line of reflection, according to this, is going to be equal. And if you'll notice, it's showing that it makes a 90-degree angle, which makes it perpendicular. So the line of reflection, this line of reflection is going to be a perpendicular bisector of a segment connecting a point on the pre-image to the corresponding point on the image. So this is showing me that this distance and this distance are equal. This line of reflection is perpendicular, so therefore it's a perpendicular bisector because it cuts this distance in half. So the line is perpendicular, and then of course the points, if I were to draw them here, identifying this intersection, I better use a different color, right here, here, and here, and let's say we'll call this point D. That's not very good. Point D, point E, point F. And so we know, looking at this, that point F is going to be the midpoint of the line connecting A and A prime. That line segment, F is the midpoint. E is going to be the midpoint of the line segment connecting B and B prime, and then D is going to be the midpoint of C and C prime. And you can see here by their congruency that this segment from C to point D is going to be the same from C prime to point D. That distance is going to be the same in corresponding here and here. So that's just some of the characteristics of the reflection, and we haven't really talked about the concept of this really, but if these lines are all parallel, if these segments are perpendicular to my line of symmetry, or line of reflection, that makes those parallel to each other. And we're going to go over some of these examples here, but just so we know that in those characteristics that we're looking for. And so here, if we look at it, and another example, and I will make it a little bit larger so we can use it. And in doing so, let's see here. If you were told that triangle A prime, B prime, C prime is a reflection image of triangle ABC over line L, so here's my line of reflection, then you know that L is perpendicular bisector to segment B and B prime, A and A prime, and C prime. So if this is a line of reflection, some of the things that I'm going to know is I'm going to have, this is line C prime, segment B prime, and segment A prime is going to be right here. Then we know that it tells me that they're a perpendicular bisector. So then that means that I have a 90-degree angle from these segments to my line of reflection. And then remember that if it's going to be a perpendicular bisector, that tells me that these two segments are equal. It tells me that this segment is equal to this segment, and it tells me that this segment is equal to this segment. So we're able to identify some characteristics of that. And I'm going to use an example here, but just being able to identify that. So if I know that the distance from, call that point D, if I know that A prime D is 10, then, what does AD equal? So this value right here. Well, those are going to be equal because of my congruency marking. So AD is also equal to 10. So these are my identifiable characteristics. And then if I were to give another example, that if, let's see here, if I have point E, and I know that this segment is going to be 2x, and I know that this segment is going to be 6, I know that BE is equal to B prime E, and if I do some substitution here, I know that BE is equal to 6. 6 equals 2x, and if I were to try to solve for x, do my inverse operations, and it turns out that x is going to be equal to 3. So I'm able to use some of those characteristics and those definitions to identify information. Now that we, of course, reflections are described using a rule that shows how each coordinate in the pre-image is mapped to its image. And what you see here is the rules for reflections. So when we are talking about reflections across the x-axis, if you notice here is as we reflect across the x-axis, our pre-image is xy, and then it maps to x negative y. So what does that mean? If you look here as an example, point A is actually going to be, looks like it is going to be 2, 3. Now if I map it across the x-axis, so it's going to be 1, 2, 3. My new A prime is going to be now, the ordered pair would be 2, negative 3. So if you see what changed, my y value changed from a positive to a negative, and that's what's saying here, that over the x-axis, my y value went from positive to a negative. Let's see what's next. So we'll say that this was A, and let's look at B. So if we reflect over the B, the y-axis of point B, so we'll pick this point right here will be B, and my ordered pair is going to be 1, 2. And if I reflect across the axis, it's going to come to negative 1, 2, and that is again going to be B prime. And so it looks like the only thing that has changed is my x value. And if we look here, when we do our thing, when I reflect over the y-axis, my x and y become negative x and y. So there you go, we saw the negative change because the value of x changed because we crossed over the y-axis into the negative region. Now, this one's going to take a little bit, this one will be a new graph, and we're going to talk about reflecting over y equals x. And that is going to be the this imaginary line right here. So that is y equals x. And it says that if we reflect over y equals x, then the x value becomes the y value, and the y value becomes the x value. So if we look here and we say 1, 2, 3, 4. 1, 2, 3. Change that. Fix that a little bit. 1, 2, 3, 4. And then if I look at my reflecting, if we create a point, so I have point this is going to be point C, and its ordered pair is going to be 4, 2. And then if I reflect it across the y equals x, we're going to have point C prime, which is going to be 0.24. So we can see that my x and my y's have switched as we get right here. That was point C. And then x equal, the line over x equals negative x, y equals negative x. So as we make that reflection across y equals negative x, which is this green line here, and it's a -1 slope. And then if we start off with D and we start off at 3, -1, and I reflect over this line, I end up at 1, -3, which is a reversing. So -y, -x. So there you just basic rules of reflections and mapping, and this will become more familiar as we practice it, but those are the basic coordinate plane reflection